Hello, welcome back to another video on Science 10. Today we'll continue to take a look at energy flow within our biosphere. Today we're going to take a look at the phase change of water. Previously, you have looked at, of course, the original source of our energy in our Earth come from the sun. We took a look how the global trend of energy flows through convection and through the Coriolis effect. Then we look at local, how water may have an impact on our climate. But within a local system, we can also think about how water may absorb and use up energy in different ways. Okay, one thing we would like to talk about, of course, is the water cycle. Okay, which is a very important process through the hydrosphere. Okay, the water cycle, otherwise known as the hydrological cycle, the water changes phases. Okay, so initially, of course, it's most common that we probably experience is liquid form as water, and then when the sun's heat gets absorbed, it evaporates, turns into air. Okay, water vapor, and then when it reaches colder temperature in the stratosphere or upper, I should say not stratosphere, upper troposphere, the cloud condenses into liquid again. When there's enough, it falls back down onto sometimes onto colder regions. It freezes, okay, from liquid to ice, and then the liquid is gonna melt. The melt becomes water and flow back down to the river, and then get evaporated, and the whole cycle continues. Okay, so this is the water cycle we all know well. Just into that description, we already talked about multiple process of conversion: liquid to gas, gas to liquid, liquid to solid, solid back to liquid, and then the cycle completes. Okay, through all of that, there is energy being used up during that process. Okay, when water change phases, okay, energy is either released or absorbed. You can probably have a guess which one is which. Yes, when you are actually becoming liquid, when it's melting, or when it's evaporating, right? When it's becoming less dense, you absorb energy. You heat the water up to evaporate it. You heat the ice up to melt it. On the other hand, when you're freezing something, you release energy or take away energy. If you want, you cool a water down to freeze it, for instance. Okay, so that's a process. That's how energy is changed during that. Okay, you would make sense the amount of energy required to melt ice should equal to the amount of energy freezing water, thanks to a very famous law we have worked with in physics. Hopefully you remember, the energy gain and loss should be equal for the same relative phase change. Okay, so the three forms of H2O, water. You have ice, water, and vapor. The process of freezing is called fusion. Okay, so fusion and evaporation. All right, and the process of fusion, okay, requires a measurement called heat of fusion. Here, it's the amount of energy for 1 mole of water to change from solid to liquid. It's 6.01 kilojoule. That's quite a bit for 1 mole of water. Okay, the heat of vaporization is the same concept, except it's for evaporation. Okay, or vaporization. Okay, which is 40.65 kilojoules for 1 mole of water to change from liquid to gas form. Okay, the opposite process, okay, it's called condensation. Notice the number is the same, but because just like our calculated specific heat capacity, absorption is positive, negative means release, right? So the number is the same for heat of condensation. The number is the same. Same thing for freezing. The number is the same, but the sign is negative. Now, it would make no sense for us to remember a positive one and a negative one. We just remember which process it should be positive, which process it would be negative. So we only remember the heat of fusion and heat of vaporization, and just add a negative sign if the process is going in reverse. So if you want, in summary, this is the diagram. You might notice there is technically possible to go from solid directly to gaseous form. We'll not look at that in Science 10, but in Chemistry 20, it's a process that will be investigated. So, in order for temperature to increase or decrease, the kinetic particle of the energy of the particle has to increase or decrease. But during a phase change, you're not changing the movement of the particle. You are just you're only changing excuse me, you're only changing the spacing between them, in a sense. Okay, so here's the key. During a phase change, maybe I should highlight it. During a phase change, this is a very common misunderstanding. During phase change, there is no change in temperature. Okay, because, like I mentioned, it's not being converted into the kinetic energy of the particle. Okay, it's used to change the state of it's moving it. Okay, it's not changing how fast it's moving. If you want, it's only changing the structure it's moving in. It's not actually changing its speed. If it's not changing its kinetic energy, then there's no change in temperature. All you did is change state. So phase change, no change in temperature. But energy is still added. Okay, thermal energy is added or absorbed or released as a process of breaking those bonds. Okay, so energy is actually there to the structure we call bonds. Okay, we'll actually break the bonds between water molecules so it become different states. We're not changing the movement of the molecules. The molecules move away. We just not allow them to move more freely or more restricted, depending on which process it is. All right. So to formally define these concepts, heat of fusion is the amount of energy required to when 1 mole of substance change from solid to liquid. You'll read the rest. You read the first one. Everything else is the same. It's the same idea. Okay, same idea. Fusion, solidification are opposite. These are opposite of each other. Condensation and vaporization, of course, are opposite of each other. They should be equal up to a sign. Equal up to plus or minus. Okay, same thing with these two. For the same substance, of course, for the same substance. And to calculate the heat of fusion or heat of vaporization, or I should really say calculate the energy required to convert. Okay, you just see the heat of fusion is the energy required to freeze substance divided by the number of moles that's being frozen. The one you probably see more, also very common, which probably is equal to N times the heat of fusion. The energy of fusion, I should say. Energy of fusion is equal to number of moles times the heat of fusion. Heat of vaporization is exactly the same thing. It's a definition. It's not a complicated formula. It is just within a definition. Okay? Energy required to vaporize is equal to the amount you have to vaporize times the amount of energy vaporized per unit mole. Okay, per unit mole. All right. So once again, here are the definitions. I wrote over my commentaries, but just remember those formulas are there. Just simple rearranging. Okay, simple rearranging. Okay. Once again, we decide whether it's positive or negative depending on the situation. Okay, depending on the situation. Okay, so remember that we have learned multiple formulas: fusion, heat, specific heat capacity, and heat of vaporization. What does it look like on the heating curve, which is temperature over time? Well, when temperature is negative 20 degrees, of course it's ice. It's going to warm up at 0 degrees. Notice during 0 degrees, there's a moment where its temperature is not changing. This is when ice and water are mixed. It's melting. Here it's melting. Temperature, once again, does not change when ice is melting. Temperature does not change. While it's in liquid between 0 degrees to 100 degrees, during that process, the water is a liquid. There's no phase change. Then we use specific heat capacity. Okay, we can calculate the temperature change of water. Remember, water, not ice, not steam. Okay, water using our formula for specific heat capacity. Okay, there is temperature change when there's no state change. Of course, we want to reach 100 degrees Celsius. There's another state change into steam. Once again, see, it's flat temperature, no temperature change again, no temperature change. Okay, be careful. You don't want to make that mistake. Okay, there's no temperature change when it's melting or when it's evaporating or when it's condensation or freezing freezing. That's right. Okay, when it's solidifying, if you want. Okay, so remember, no temperature change when those processes are happening. All right, so that's what I'm trying to say overall. Okay, all surrounding heat is used to change ice to liquid and vice versa without heating it up. So here's the problem. When 0.751 kilojoules of thermal energy is added to 0.125 moles of ice at 0 degrees Celsius, the ice changes phase. Okay, calculate the, there's a word here, experimental heat of fusion. If it says experimental, you cannot use your formula. You actually have to calculate. Okay, actually have to calculate. Experimental means use data provided in question. Use numbers from question. So you cannot say, oh, heat of fusion of ice. I know that's blah, blah, blah. You can't do that because that's not experimental. That is, everything we talked about is theoretical. We're just going to use our formula here. Now, we're asked, well, let's make a list of variables first. First, we'll be asked experimental heat of fusion. So we're asked heat of fusion. We don't know. We were told 0.75. That's 0.751 kilojoules of energy is added to melt the ice, right? To melt the ice, which means that is 751 joules. Remember, that's the unit we have to work in. Temperature does not matter because it's melting. So T doesn't matter. It should be 0 degrees. Doesn't change. So we don't care. We also know that the number of moles is 0.125 moles. Plug in our formula. Heat of fusion is equal to the energy required to fuse divided by the number of moles. We know it's positive once again because it's added, so it's positive. So heat of fusion is almost made a mistake. 751 joules. I didn't make a mistake. Haha. Heat of fusion is what are we looking for? Spoilers. Keep clicking the highlighter. So heat of fusion is equal to 751 kilojoules. Not kilojoules, just joules. Divided by a number of moles of 0.125 mole. We plug that into the calculator. Let's quickly do that. And we get 751 joules divided by 0.125. And I got 6,008. So I should 6,008 joules per mole, right? Joules over mole. But this is the wrong sig dig. So we should correct it to correct sig dig, which is 3. So 6.01 times 10 to the 3 joules per mole. If you're going to calculate more, of course, we're going to have to use 6,008. but we're not calculating more. This is our answer, so we should record with the correct sig dig. Kilojoules per mole. All right, so that's the heat of fusion of water within the context of this question, the experimental heat of fusion. All right, so that's a very straightforward use of this formula. I could ask something a little bit different. Okay, this one is not experimental. You can use theoretical value. How much thermal energy is required to completely melt 3.20 moles of ice at 0 degrees Celsius? Remember, melting means absorb energy. Absorb means, once again, the energy is positive. Okay, how much thermal energy? Well, let's make a list again. How much thermal energy? So we're looking for Q of fusion. The amount of thermal energy is Q. We know the number of moles is 3.20 moles. And the heat of fusion for ice, right? Ice to water is fusion, or the opposite of fusion. It is fusion. Okay, freezing is the opposite of fusion, which is solidifying. Okay, heat of fusion, we know it's 6.01 kilojoules per mole. Convert to the right unit, of course. Heat of fusion is 6,010 if you want. I'm not going to do that. Times 10 to the 3 joules per mole. That's the unit we want to use it in. Okay, so that is heat of fusion. So once again, we'll write down our formula. So the energy required to melt the ice would be number of moles times the heat of fusion. Just simple rearranging, but multiply n to both sides. Okay, be careful. You can only do this because n's in the denominator. N and n cancels. So Q of fusion is equal to the number of moles. It's 3.20 moles. Times heat of fusion is 6.01 times 10 to the 3 joules per mole. I just realized we do not have to convert to joules, but it's a good habit to do the conversion because you never know. So 3.20 times 6.01 times 10 to the 3. And I got, with correct sig dig, straight to the answer, by the way. I'm trusting you can calculate and round without going through the process. 1.92 kilojoules per, no, not kilojoules per mole, just kilojoules, because the mole and the mole cancels. Just 1.92 kilojoules. Okay. Mistake, not 1.92, 19.2. I was surprised there. Wait a second. 19.2. There we go. That would make sense. 19.2 kilojoules. So that's the amount of energy required to completely melt that much ice. All right, we'll do one more example. Okay, and I'll show you some sample questions which you could try. All right, but remember, we can mix it up. It's moles, right? We can use molar mass and actual regular measurement, which is mass, gram, and calculate our problem instead. So here's an example like that. Calculate the amount of thermal energy required, just like before, to change 500 grams. Okay, we're using mass now of water from liquid phase to vapor phase. The molar mass of water, okay, the molar mass of water is 18.0 grams, okay, per mole. And the theoretical heat of vaporization of water is 40.65 kilojoules per mole. That's given to us. We don't have to use theoretical. Okay, I would recommend you pause the video and try it yourself first. Oh, hopefully you tried the video yourself already. Pause the video and try it yourself already. We're now going to go through it. So once again, make a list of variables where I'm looking for Q. Here is change water to liquid, so it's vaporization. Liquid to vapor, it's still positive, so we expect our answer to be positive. All right. Now we are given that the mass is 500 grams. The molar mass, capital M, is 18.02 grams per mole. And of course, we know the heat of vaporization. Remember, once again, it's liquid to vapor, so it's positive. This one I'm going to make a distinction here because if I ask you about vapor to liquid, you would put negative there. All right, so this is our list of variables. Start with what we're looking for. The heat of vaporization. I will trust you can rearrange the formula, no problem. So I'm going to do that too. The amount of moles times the heat of vaporization. This I know, but I don't know what N is. Okay, so find N. Find N. I don't know why my hand shaked and draw the line diagonal, but that is okay. There we go. Let's change color. Change color of the pen to find N. All right, to find N, we're going to use our molar mass, of course. N is equal to the mass divided by the molar mass, right? The amount of stuff is there divided by how many moles for each gram of object. So molar mass. So N is equal to 500 grams divided by 18.02 grams per mole. Grams cancel. The mole would come on top because double division is multiply. So when you multiply that out, take out calculator. 500 times 18.02. Not times, divided by 18.02. And I got 27.746,947, etc. moles. Okay, I didn't round. Okay, as you dot indicate I did not round. Okay, I'm going to remember that number and use that. So heat of, change the color back. So substitute it back into our equation here. So heat of the energy required to vaporize the water is equal to 27.74694, etc. moles multiplied by heat of vaporization, which is positive 40.65 kilojoules per mole. It may be helpful to convert it to joules, but I'm going to not do that here. So multiply them out. Remember, use exact values. Do not round. Use whatever digits you have on your calculator. So I'm going to use that, multiply by 40.65 kilojoules per mole. And I got an answer with the correct sig dig of 3 once again from 500 grams. So we get heat energy required to evaporate that much is 1.13 times 10 to the 3 kilojoules. Actually quite a bit. Okay, quite a bit. All right, you can use megajoules if you want, but I'm going to leave it like that. So that is the answer for question. Slightly more complicated, but not really. Okay, not really. As long as you are careful. Okay, as long as you are careful when solving this problem, make sure the units are consistent. Do not round and go through the process carefully. Okay, calculate the moles using molar mass and then calculate the energy required to vaporize or whatever you need. Okay, combining multiple process you have learned before. All right, so this wraps up our example involving heat of fusion and heat of vaporization and energy change within phase change of water. I'm gonna quickly go through each questions. I would like you to try on your own. Okay, you can feel free to pause the video and take a look, but I'm just gonna go through them very quickly. Another one, okay, it does have a textbook page number on there for you to look at if you do have the Pearson Science 10 textbook. So this is one of the questions. It's another one, good idea to try. And another, it's different. It's not water anymore. It's methanol. So you get to use the formula for some different context. Okay, different context, not just in our climate, but in chemistry in general. Another one, and that's it. You look. You got a peek at the other one, and that wraps up the energy change, the energy flow within our biosphere. Okay, so how energy is transferred, which is of course through convection and the Coriolis effect primarily, and in detail how to actually calculate the heating up and cooling down of object, as well as changing of phases. Okay, in our next video, we have learned the process. We have learned the process through which energy are transferred. In our next videos and next lessons, we'll take a look at various different climate and climate conditions and land and the weather patterns we would expect. Okay, weather patterns we expect at various different climates. Okay, and we'll learn a new technique of analyzing those different climates, something called a climatograph. You may have heard of it. But that's to come our next lesson. And with that, thank you for watching. I hope you have a good day.